Welcome to qnawire.
We want to determine the characteristics of the radioactive mixture. Let's find our minimum number of different nuclides present. We can observe our different decay rates over time. So we see that they decrease over time. We can look for significant drops in our decay rate to answer this question. We see one between 0.5 hours and 1 hour, and another one at 1 hour and 2 hours. This could suggest that there are at least 3 different nuclides present in our mixture. So at least 3 different nuclides present in this mixture. Now we want to find the half-lives. We identified 3 significant drops. Let's go ahead and find the half-lives. So for our first nuclide, we had a decay rate at 4120. For 1 hour, we have 2570. And so then our half-life is 0.5 hours. For our second nuclide, we have a decay rate at 2570, another at 1350, and then our half-life of 1 hour. And then for our third, we have it between at 1070, at 3 hours, 872, and then our half-life is 0.5 hours. So these are our different half-lives, 0.51 and 0.5 hours. How many nuclei are initially present? To determine that, we can use our decay equation. N as a function of time is our initial number of nuclei, e to the negative lambda t. So for our first nuclide, let's find our lambda, which is ln2 over our half-life. We get 1.38. Now we can plug in 7500 equal to n naught e to the negative 1.38 times 0. So n naught is 7500. For our second nuclide, we do the same, and so we get n naught 2 to be 2570. Then we do it for a third nuclide, n naught 3, we get 1070. So these are our initial number of nuclei for each nuclide. For D, how many of each type are present in 5 hours? So we can use our formula again, n at 5 hours equal to 2570, or not 2570, but this will be our n naught, 7500, e to the negative 1.38 times 0, we get 7.23. For our second nuclide, n at 5, we get 81.3. And finally, for our third, we get 1.03. So these are how many nuclei are available.